In this video, we will be talking about one lesson in statistics that's usually introduced in grade 11 STEM. This is the comparison of two means that are independent samples. And yeah, there are lessons before this, but then I've decided to make a video first about this. I'm not sure if I'm supposed to send some of those videos because some of the words are said in Filipino, but then yeah, I'm pretty sure that most of it could be understood by the English audience, but yeah, those lessons are fairly easy since they're basically about yeah, anything that revolves around this formula, that's statistic for a mean, wherein the standard deviation is known, this one. I'll be mentioning this often. This symbol, I call it the onion symbol because it looks like an onion. So just to make things easier. And there's another formula that's used wherein given that the onion symbol is unknown. So yeah, this time we replace the onion symbol here with S, that is the sample standard deviation. And there is a third formula for one sample hypothesis. This is the test statistic for a proportion, wherein if in the previous two formulas that I showed you, this is the population mean. For this formula, we have its counterpart as the pi o. So yeah, this is the formula. I've made videos about that already, except for this one though. I might make one after this. So yeah, let's start with the actual lesson right now. Comparing two means, independent samples. Let's redo example 10.1. By the way, the ebook that I'm basing this lesson on is ultimately called Applied Statistics in Business and Economics. So yeah, in our school, we're privileged to use the book for our review, and yeah, I'm glad to have it. So let's start with 10.1 again. Drug prices in two states. So particularly for one sample hypothesis, we have something like this. It's important to take note of these formulas, especially when you're trying to answer problems related to the lesson. There you go. Wait. Okay, better. So yeah, you might want to screenshot this paper. This is it's gonna help a lot, I can assure you that. So back to the question, to the practice problem. We have to enlist the following. So first is our A variable. This is the level of significance. We have x bar 1 and x bar 2. Because we're comparing two samples, we're gonna have two sample means. We have S1, S2, N1, N2. As always, the N variable is the sample mean. I'm not sure though what S2 is, but then yeah, we'll be having more on that later. This is the table. So basically, this is everything that we have to know to finish the given, to finish writing them. So for x bar 1, we have 133.994. For x bar 2, we have 138.018. For S1, we have 11.015. S2, we have 12.663. N1, we have 16 pharmacies. N2, we have 13 pharmacies. So yeah, we'll make this table small because our solution will be a lot, as in a lot. So these are everything that you're given. Now, based on the paper that I showed you a while ago, we have 3 cases when trying in the lesson about independent samples, 2 independent samples comparison, or this one, comparing 2 means independent samples. So the first case is where your variances are known, O1 and O2. And for case 2, unknown variances, but they are assumed equal. Case 3, the same thing, unknown variances, but this time they're assumed unequal. So yeah, the formulas of case 1 and case 2 are, case 2 and case 3 are the same, but then the only difference is that in case 3, because there is an assumption that the variances are unequal, that means S1 and S2 are different. For case 2, they're the same, by which there is a specific formula to compute for SP raised to 2. So yeah, the question is now, how will you be able to discern which case is relevant to a certain scenario or to your practice question? For this in particular. But yeah, let's be more general for the moment. Case 1, you know that a certain scenario is case 1 because the sample size, or in other words, the n variable is large. So let's say n1 is, there's a standard. As long as your n1 is greater than or equal to 20, then your sample size is large. So let's say n1 is 30, n2 is 765. This is only an example. So yeah. Case 2. You know that it's case 2 if n1 and n2, those two variables are roughly equal to each other. Doesn't have to be equal to each other, but the more equal, the better. But then if, let's say, n1 is 12, n2 is 13, they're roughly the same. So case 2, unknown variance is assumed equal. This is most likely case 2. Okay, sorry, the rice cooker alarm. Anyways, for case 3, n1, n2, by the way, we know that the n is small if this time it is less than 30, as you can see here. So for case 3, unknown variance is assumed unequal. It's still the same concept as case 2 in terms of n1 being roughly equal to n2, but then s1 and s2 are far from each other. So let's say s1 is 15, s2 is 42. So they're very far numbers from each other. So yeah, that's it. Those are important assumptions that you have to know. So for example 10.1, how do you know which case this is? But before that, let's determine which tail test is applied in this situation. So at A is equal to 0.05, is there a difference in the mean for all pharmacies in Colorado and Texas? Is there a difference? That's the keyword, difference. So for difference, that is two-tailed test. Okay, and yeah, which case is this? So provided that N1 and N2, I think they're roughly the same, don't you think? 16 and 13. Although the three number difference, it might be significant. It's the claim may be debatable, but then for S1 and S2, they're roughly the same. And there's one thing that you have to know also. N1 is less than 30. 16 is less than 30, as well as 13. That is N2. So this is most likely case 2. Considering that the S variables are also not that far from each other, these two define these two define case 2. So it's not case 3 because S1 and S2 are roughly the same. If let's say S1 is still the same number, but then S2 is, let's say, 74.015, they're very far from each other. So most likely we use case 3, but that's not the case for this one. It's case 2. Why isn't it case 1? Well, the reason why is that, well, obviously for case 1, the requirement is that you should know that n is greater than or equal to 30. But that's not the case for this one, as you can see here. Okay, so we have settled the fact that it's case 2. Let's rewrite the formula. By the way, for case 1, we use, because it says there is zcalc, we use the z-table to find the critical value. Of course, in a zcalc or in a z-table, you need to look for the a variable and the tail test type in order to determine the critical value. You use, in other words, the standard normal distribution. For case 2 and case 3, as you can see, they're both t-calc. So they use the t-table in order to determine the its critical value using a and the degrees of freedom. So more on that later about the degrees of freedom. There are 3 kinds of formulas for that. One is n minus 1. This is for the one sample hypothesis test. Actually, yeah, let me just discuss it for a while. One sample hypothesis test. But if you do want to go straight to the example that we're about to answer, feel free to skip this part. But yeah, let me just show this to you. df n1 plus n2 minus 2. This is 2 sample hypothesis test. For a while, someone's at the door. Okay, given that the degrees of freedom is wait, I'm not sure what this lesson is about, but then for the degrees of freedom we're in, n is it's equal to n minus 2. This is a very recent lesson. I think it's about it's still one sample, but then it eventually changes over time. I'm not sure about that one, so I'll just say most recent lesson. I think that's around chapter 12, around pages 470 of our book. But yeah, more on that in the next videos to come. But for now, we know that it's case 2. Let's rewrite it. Tcalc is equal to x bar 1 minus x bar 2 divided by the square root of sp raised to 2 over n1 plus sp raised to 2 over n2. So let's start substituting the values. Oh wait, by the way, before we do that, I'm so sorry. Let's try the first step first. Basically, the first step is determine the hypothesis. So HO, H1. HO is the null hypothesis. H1 is the alternative hypothesis. And right now, we have, since this is a 2-sample hypothesis problem, we involve the use of U1, U2 instead of just U0. U0 is only used in one sample hypothesis tests. So U1 minus U2, U1 minus U2. And then since this is a two-tailed test, our inequality signs will be these two. Equal sign for the null hypothesis, and then alternative hypothesis will have the not equal to sign. So remember that these things go together. They don't change at all, regardless of what formula you use. But then only this one, for this one, it basically defines the fact that this is a two-sample hypothesis problem. So what do we copy next? Well, we just write 0. for some reason. Don't have to ask why, it's just 0, I believe. Yeah. And then let's find the critical value first before we proceed to step 2. Critical value, wait, this is a t value, not just any value. It's a t to be specific. So what do we need? Since this is a t-calc kind of problem, we use the t-table. We need the a, but this time it's a two-tailed test, so a over 2. So 0.025. And then you need the degrees of freedom, df, since n1, n2. This is the formula of our df right now. Two sample sorry, so not hypothesis. No, not hypotenuse, it's hypothesis. N1 plus N2 minus 2, that is 16 plus 13 minus 2. 16 plus 13 minus 2. I don't have my calculator right now, let me get it. 16 plus 13 minus 2, we get 27. So provided the degrees of freedom is 27 and our a value or the level of significance is 0.025, originally 0.05 because it's a left-tailed test, we get 2.052. How do you know if this is a positive or a negative or a positive negative? Well, because it is a two-tailed test, we write plus minus. These two go together. If it's right-tailed, then it's positive. If it's left-tailed, then it's negative. So, with that, critical t-value, let's say step 2, reject HO if, this is standard, you always write this. Reject HO if t-calc is less than or equal to 2.052 or t-calc is greater than positive 2.052. So in a two-tailed test, always know that these are standard. So given that your critical t-value has a plus minus symbol for the value itself, you write the statement 2 like this. Or I mean the statement in step 2. So number 3, our favorite part, the computation. So let's start subbing the values together. 133.994 minus 138.018 divided by square root of, oh wait, by the way, I've mentioned this a while ago. I forgot to actually execute it. Let's use this formula first, sp raised to 2. You have to find sp raised to 2 first. Yes. Oops. Copy paste this formula. Okay. So sp raised to 2, n1 is 16, n minus 1, and then s1, that is 11.015, and raised to 2, plus n2, which is 13, and minus 1, and then s2 is 12. Oh my gosh, we lack so much space. This is exactly what I was talking about a while ago. 12.663, then raised to 2, divided by n1 plus n2 minus 2, as you can see here. And then put all these values in the calculator. Eventually, we would get 138.673. Sorry, I've already answered this problem a while ago when I was teaching a fellow classmate of mine. But then, yeah, we got the right answer. Yeah, I can agree that it's kind of stressful to, it takes a lot of time to input all of these in the calculator. So, yeah, once you do it, you don't have to do it again. sp raised to 2, so 138.673 then raised to 2. If you're wondering, this is exactly the same number as this one. Why do we have to raise it to 2? Well, for some reason, yeah, you have to do it. You have to raise it to 2. Otherwise, you will yield a different answer, which is something that we wouldn't want to have. So, apologize if I don't have any definite explanation for it. My statistics teacher doesn't really elaborate much on that. Or maybe I wasn't just listening. I don't wish to offend anyone, but then, yeah. This is how I understand the lesson. This is how I'm going to teach it, which is proven correct. Still proven correct. So, TCalc, eventually that's going to be negative 0.078. So that is for step 3. Step 4, one easy way to analyze if whether or not we reject the null hypothesis or the HO, we can draw something like this. And because it's a two-tailed test, we write on both sides this something like this, 2.052 and negative 2.052. And then we write, we plot the location of the TCalc, which is negative 0.078, somewhere over here. And this is do not reject. And this region is reject, other side is reject. This is standard for all two-tailed hypothesis diagrams. I'm not sure what this thing is called, but then yeah, it's something related to statistics. So, what is our ruling for step 4? What's our final resolution? Because it is in the do not reject region, we do not reject, or in other words, fail to reject HO. Yeah, exactly the same answer. So what does HO suggest? We don't reject HO. Well, to start with, HO is initially the null hypothesis. So what is the definition of a null hypothesis? Basically, there is no significant change. In the context of a two-tailed test, there isn't any significant change. So to answer the question here earlier, at A is equal to 0.05, is there a difference in the mean for all pharmacies in Colorado and Texas? So, in other words, is there a difference? Do we reject HO? As a response, we do not reject HO. That means there is no significant difference. So, yeah. Alternative hypothesis is H1, which basically states that there is a significant difference. But that's what we don't accept right now, since we embrace HO. We don't reject it. If we reject it, that means we're embracing the alternative hypothesis, claiming that there is a difference. Might be confusing at first, but yeah, it will eventually sink in the mind as we answer more practice questions. So let's answer more on this chapter. This is actually chapter 10.2 of the ebook. So we're answering real life math problems based on this ebook. I really do hope that this ebook is popular. So, okay. Geez. Let me double check something that I've answered before. Pretty sure. Wait. 10.3. Yeah, I'm planning to answer everything in this video as much as possible. So this is what we did. Example 10.1. 10.3. 10.1 again. And then 10.2. Okay, this is from the organic chemistry tutor. Yeah, I support his channel. 10.3, 10.4, 10.5, 10.6, 7. Bro, I can't believe I have answered everything before. But then, yeah, I can assure you, I cannot assure you that all of those are correct. Let's start with no, we'll start with 10.2. 10.1, we can't because uh, obviously, not exactly obviously, but then our teacher told us that the calculating for the p-value isn't part of our syllabus. So we only stick to the t value, the t value, the z value, and other else that's relevant to the topic or to the lesson. 10.1 is not part of it, not part anymore. So 10.2, 10.3, 10.4. Okay. Kindly skip this part if you wanna get um, to the solutions themselves. This might take some time. It takes a lot of time to crop stuff. As you might already have realized, it takes me a lot of time to crop, so might as well do it during the recording. Oh, yeah, you know. We can't do 10.2. I think, yeah. It says calculate about the p-value, when that's not part. We'll go 10.3. Okay, let's start with 10.3. Is there a difference in the number of years between returning part-time seasonal employees? Let's cut to the chase. Write down the important stuff. So again, in a two sample hypothesis test problem, we enumerate the following. We are looking for the following as a given. So yeah, S1, S2, N1, N2, X bar 1, X bar 2. X bar 1 is wait, from a random sample of 101 turning part-time. So sample of 191. This is the first sample size that's mentioned. So that's definitely N1. N2 is 833. That comes from this as a second one mentioned. Second random sample mentioned. And the average seniority or X bar 1 was 4.9 years. So that's 4.9 years with the standard deviation S1. Now I understand. S1 is standard deviation. Took me some time to realize. Anyways, equal to 5.4 years. Random sample GG. This is 7.9. Sorry, this is 7.9 years X bar 2 with a standard deviation S2 equal to 8.3 years. You don't have to write years anymore. Yeah, I don't think you have to. And then our A value, the level of significance, is 0.01. Okay, we have everything that we have to everything that we need to start already. So step 1, hypothesis, the hypothesis, the null and alternative, HO again, and we use U1 and U2. By the way, let's determine first which type of tail test this problem is. Assume the population variances are not equal. Okay, this may suggest what case we're going to use. Which among these three we'll be using. So test the hypothesis. Okay. Is there a difference there? In the first sentence, it's stated that. Is there a difference in the number? So again, the word difference, this may suggest that this is a two-tailed test. Is there any significant difference? Okay. And then, yeah, two-tailed test. We have an equal and a not equal to sign. And then we just write 0. And then to look for the critical, wait, let's determine first what case this is. Assume that the population variances are not equal. What does that suggest? Which here is population variances are assumed unequal. So I bet that's case 3 already. I think. Wait a minute. But then at the same time, even despite this being stated, this may suggest this is case 3. But then there's also another idea that we have to recall again. For case 1, this is what we use if the n1 and 2, they're both greater than or equal to 30, by which it's true. 191 is greater than 30. 833 is greater than 30. So most likely this is case 1. I'm not sure though why the book stated that we have to assume population variances are not equal. Or maybe they're connected with each other. Maybe. But for now, that's not how I understand it. We know that n1 and n2 are greater than 30, so we use case 1. So what is the case 1 formula? This is the only this is the only formula wherein we use the z table to find the critical value. Unlike case 2 and case 3, this is zcalc. So zcalc is equal to, just copy paste the formula, or I'll just write it again by scratch. X bar 1 minus x bar 2 over square root of O1 raised to 2 over N1 plus O2 raised to 2 over N2. This is the formula. X bar 1, x bar 2, 4.9 minus 7.9. And then the square root. Oops. I'm gonna need a lot of space. O1 raised to 2. Wait a minute. Let me double check 10.3. Which case do we use? I wonder. They still used case 1. But then it's stated in the question that we're going to use the S variable instead of the onion kind of variable. That's something that I would want to ask my statistics teacher, but apparently she doesn't reply. Partly because I believe it's my fault, but yeah. She doesn't want to reply because I keep spamming her. Anyways, sorry. S1 is 5.4, so 5.4 raised to 2 over N1, that's 191. And then S2, that's going to be 8.3, and then we put the raised to 2. And then we put 191. I'm sorry, 833. Put these values in the calculator. What will you get? We get negative 6.184, I think. Is it G so far? Yeah, we're on the right tracks. Zcalc is equal to negative 6.184. And yeah, before that though, we haven't even discovered the critical value yet. Critical Z value. How do we get it? We use standard normal distribution methods. That means we determine, we need the A variable and the fact that it's a two-tailed test. So because it's two-tailed, again, our A should be A over 2. So 0.01 divided by 2 is equal to, wait, let me get my other scientific calculator. We have 0.005. So 0.005, two-tailed test, what does it indicate? I have another sheet that we should base our solutions upon. Let me picture something again. Okay. And yeah, given that we have 0.01 as our level of significance, it's gonna be 0.05, and this is a two-tailed test. So this is what we use. We use plus minus 2.576. So as you can see here, two-tailed test, all of the symbols are plus minus. For left-tailed test, all of them are negative. For right-tailed test, all of them are positive. Okay, so you might want to save this paper also. It's gonna help a lot. I'll just, yeah, screenshot it anytime you want. Yeah. Back to the solution. Now that we know the critical z value, let's look for the statement. So reject HO if z calc is less than negative 2.576 or z calc is greater than positive 2.576. So yeah, again, for two-tailed test, this is standard. To memorize this, just remember, imagine that this is an arrow to the left, and then this one is an arrow trying to hit a positive symbol. So yeah, please memorize. This is basically step 3, the one we did earlier. We were too excited to compute. So yeah, negative 6.184. Let's see. Let's determine what's our final resolution. We know that our critical z value is negative 2.576. So this one is positive 2.576. And this one is negative 2.576. And then this region is negative 6.184. Just imagine this is a number line. These are the negative integers, these are the positive. Basic math. And then, yeah, there's a principle that in a two-tailed test, this region is do not reject. Again, I'm just reiterating what I mentioned earlier. This is two-tailed test. This is also a two-tailed test. So what's our ruling for step 4? We reject HO. That's it for 10.3. Let me verify if I actually got it right. I'm sorry. Yeah, it is correct. We have the same answer as the answer key of the ebook. Okay, let's try 10.4. Oops. Oh my goodness. The developers of this application, they might have found a way to not do to prevent that glitch, because there's so much paper that isn't used yet. I only used 25 pages, as you can see there, but it's 48 already. Anyways, back to the topic. A, and then we have A, x bar 1, x bar 2. S1, S2, N1, N2. For A, we are given 0.01, X bar 1. It's okay. So produce, for example, 10 tanks of gas with 45 average MPG usage. So 45.5, sample of 10 tanks, standard deviation of 1.8. Average of same 10 tanks with 42 with standard deviation of 2.3. So assuming equal variances, I bet this is case 2. I can already see that it's case 2. Why? Because N1 is roughly equal to N2 and they're both less than 30, and the fact that it says here assuming equal variances. Isn't case 2 all about unknown variances, but they are assumed equal? These are all the same. Hence, we use case 2. That's it. Okay, we have the given. Let's start with the hypothesis test. HO, H1. U1, U2, U1, U2. What kind of tail test is this? So it says here, is the true mean MPG lower? This is a keyword for left tail test. Okay, so calculate the p-value using Excel. We're not going to do this, letter B. We're not going to do that. Only letter A. So critical, what is this? Case 2 is a T, is T calc. So critical T value, we need the degrees of freedom. By the way, back to hypothesis 1. This is left tail test. So we write this, this, and this. Anyways, degrees of freedom is N1 plus N2 minus 2. 10 plus 10 minus 2 is 18. So degrees of freedom is 18. And that A is 0.01. Because it's a two-tailed test, it's going to be 0.005. So with the degrees of freedom of 18, please kindly refer to your T-table. I hope you have it with you right now. A copy of it, digital or physical, any could do, as long as it has the complete stuff. So 0.05, and the degree of freedom is 18. So positive plus minus 2.878. So with 2.878, let's go to step 2, reject HO if T calc is less than negative 2.878 or T calc is greater than positive 2.878. For step 3, we have the computation. By the way, the formula is T calc is equal to x bar 1 minus x bar 2 divided by SP raised to 2 over N1 plus SP raised to 2 over N2. Okay, sub the values. X bar 1 is 45.5, x bar 2 is 42. Square root of, oh my goodness. We have to compute for the SP raised to 2 variable. I don't memorize the formula, but then yeah, copy paste. The perks of using online note taking. You can just easily teach this way. Anyways, N1 minus 1 times and S1 raised to 2, that's 1.8 raised to 2, plus N2 minus 1, that's 10 minus 1 times S2 2.3 raised to 2, and then basically have 10 plus 10 minus 2, that's 18. So put all these values in the calculator, and what will you get? We get 4.265, I think. We have the same answer as I can see a mistake here. I'm supposed to raise to 2. Yeah. Pathetic me. So SP raised to 2. Oh yeah, this is already the SP. Let's put it in the substitution process. 4.265 raised to 2 over n1. n1 is 10. Then 4.265 raised to 2 over 10. So the same. So 45.5 minus 42 divided by square root of 4.265 raised to 2 over 10 plus 4.265 raised to 2 over 10. We get 1.834 or 1.835 if we round it off. So that's our result for step 3. Step 4, what is our final resolution? We draw in order to find it. This is a two-tailed test again, so 2.878. This one's negative 2.878, and somewhere here is 1.835. This region is the do not reject region. So for the resolution, we failed to reject. Do I have the same? Yeah, I have the same ruling, but then in terms of the SP raised to 2, I got it all wrong. So I bet this is correct this time. Let's try 10.5. Damn, we need a lot of space. After 10.5, 10.6 and 10. Yeah, this is still a long way to go, but I might make a part 2, who knows? Oh my goodness. Okay, 10.5. Again, relist everything, all of the variables that we have to take note of. Copy, paste. Okay, what's our A variable? It is 0.01, as you can see here. What is the mean, mean amount of a sample of 17? This is the first sample mentioned, so that's 17. Was 30.47. 30.47. That's the first mean that was mentioned. With a standard deviation of 15.10. Okay, the next one is sample 14. In the same restaurant was only 1.62. And then standard deviation of 9.50. This is definitely not case 1 because n1 and n2, they're not greater than 30. So this is definitely case 2 or case 3. I bet this is case 3. You know why? So yes, we can agree on the fact that n1 and n2 are roughly the same somehow. And they're both less than 30. Besides that, S1 is not equal to S2. They are not roughly. I'm not sure if this is a symbol, but then yeah, I hope you get what I mean. They're not roughly equal. 15 is far from 9. So yeah, if it were case 2, then they're supposed to be roughly equal. But then it's not the case. So therefore it's case 3. What is our case 3 formula again? This is a t-calc. T-calc is equal to x bar 1 minus x bar 2 over the square root of s1 raised to 2 over n1 plus s2 raised to 2 over n2. Okay, so first, wait. What type of tail test is this? So at a is equal to 0.01, assuming equal variances. Holy macaroni. It says here equal variances. But for case 3, this is unequal variances. So which do we believe? I don't know. But what did I use here? I used case 2 in this scenario, but then I had a different t value. But then the ruling is that HO is not rejected. I wonder. Let's see if we could get 1.902 because that's the right answer using case 3. That doesn't make sense in this regard, but then yeah. Kindly bear with me. But for the type of tail test that we have for this problem, it says here, is the true mean higher when the music is low? This suggests right tail test. So for number 1, step 1, HOH1. So this is right, because this is right tail test, our inequality symbols would be like this. It's standard. They are always like this, regardless of the situation, regardless of what formula you use. The only difference is that for one sample hypothesis, these are supposed to be either this or this. But then for two samples, it's like this. And then we just write 0, 0. And then, what do you call this? Critical t value is what? Provided that you don't have to write for a over 2 since this is right-tailed. Look for the degrees of freedom. So 17 plus 14 minus 2 is equal to 29. Let me double check if I had the same thing. Okay. So given 29 and it's 0.01, 2.462. Positive 2.462. Why is it positive? Because it's right-tailed. So reject HO if T calc is less than negative. Sorry, I got used to two-tailed. We just copy the inequality sign that caters to the alternative hypothesis. So if T calc is greater than positive 2.462. So to the solution itself, x bar 1 is 30.47, x bar 2 is 21.62 over the square root of 15.10 raised to 2, and 1 is 17 plus what is this? S2 raised to 2, 9.50 raised to 2, and then N2 is 14. We get something like this. What is it in the calculator? 30.47 minus 21.62 over the square root of 15.10 raised to 2 over 17 plus 9.50 raised to 2 over 14. We get 1.986. Please be the same, please be the same, please be the same. Yeah, we have a similar value to 1.902. It's closer, our result is closer. 1.986 is closer to 1.902 compared to 0.149, the result that I had before when I used case 2. So it's up to you. Determine why it says here assuming equal variances, which I think it suggests case 2, but then we have to use case 3 to find the right answer. So yeah, let's visualize to find the ruling for step 4. It's positive 2.462 over here. And then we have 1.986 somewhere over here. For a right tilt test, this region is reject. This region is do not reject. Therefore, we write fail to reject HO because 1.986 lies in the region of do not reject. So to answer the question, is the true mean higher? We are not going to reject HO. So the true mean isn't higher. There isn't any significant change in the increase. I might have to cut short this video after 10.6. We still have 3 more problems in this lesson, 10.7 to 10.9. Yeah, I'm gonna make a part 2. The video might be too long already. 10.7, 10.8, 10.9. Next video. So, for 10.6, retailers in the past 20 years had to increase their stock of larger sizes. A is equal to 0.025. And in each age group, I bet N is the same. This is a right-tailed test. I think I can see why we lack some data. Let me just show you real quick. Okay, so this is what we're given. Let's say this is for the first and this is the second. Those born in 1980. Oh wait, I think we should start with the earlier year first. That's 1960. So look for the average using the calculator, or you can solve it manually if we're given this kind of given. So 8, 7.5, 8.5, another 8.5, 8, 7.5, 9.5, 7.5, 8, 8, 8.5, and 9. The average is 8.208. For x, wait, we have to calculate also for the standard deviation. That is 0.620 or 0.62. Now, let's, wait, this is 1980. Supposed to be, shoot. Okay, for the ones in 1960, let me just label that. (1960) we have 8.5, 7.5, 8, 8, 7.5 again, 7.5, 7.5, 8, 7, 8, 7, and another 8. We have 7.708. For the standard deviation, we have 0.450, or just 0.45. So we've found the data that we need, assuming equal variances. I don't think that's even any help to our situation. But anyways, this is not case 1. This is case 2 or case 3. Since the N1 and 2 they're both less than 30. And 0.45, 0.62, how do we know if they're significantly distinct from each other? Let's see. But it says assuming equal variances, so I think that's case 2. Case 2 wins. And besides, I think, yeah, they're not significantly far from each other. So case 3, dump that. We use case 2. Let me double check if I use the same case in this one. Yeah, be using case 2. I can't guarantee that this is the right answer since it's an odd numbered exercise, 10.6. There's no answer key for this at the back of our book. So feel free to point out any possible mistakes. So this is a right tilt test, so we put those inequality signs and then put 0. What is our critical? This is case 2, so t value. We have we have 0.025 and it's a right tailed. Oh, no, we need to look for the degrees of freedom. And 12 plus 12 minus 2, that's 22, I think. 24 minus 2, 22. And then the critical value 0.025, 2.074. Is positive because it's a right tilt test. Let's try step 2, reject HO if tcalc is greater than 2.074. Where do we get the inequality sign? We just copy paste from the alternative hypothesis. And then step 3, computation. Let me rewrite case 2 formula. Actually, no. I'm just going to copy paste. It's tiring, you know. Okay. Sub the values. So x bar 1, 7.708 minus 8.208 divided by, oh yeah, again we have to compute for the SP raised to 2. N1 minus 1. Yeah, just go with the flow. I think you can already understand where this is going, so I won't be speaking that much anymore. So solve, calculate. Okay, they're the same. So we have negative 4.174. Let's make our table, our graph, positive 2.074, and this region is negative 4.174. This region is reject, because this is a right-tailed test, and this one is to not reject. So our ruling is that we fail to reject HO. Okay, 10.6, good so far. Okay, I'll see you in the next video. Thank you for watching.